Welcome back everyone. In this lecture we will continue to discuss about diagonalization and Jordan canonical form etc. As I promised I will outline the proof of diagonalization using primary decomposition theorem. So, let us start. So, recall we had proved this primary decomposition theorem. Start with an operator defined on a finite dimensional space, everything over C. So, now we write the minimal polynomial as follows. It is a product x minus lambda I with the multiplicity m I, and there are let us say k distinct roots. So, then we can define this V I to be the generalized eigenspace corresponding to this lambda I. So, then using this notation one has that V is direct sum of these generalized eigenspaces V 1 etc. V k, and this is what we call primary decomposition. Now, using this we can easily prove our theorem that I stated before. So, T is diagonalizable if and only if the minimal polynomial of T has distinct roots. So, one way is obvious. If you assume T is diagonalizable, then there exists a basis B of V such that with respect to that basis you have diagonal matrix. So, let us call it mu 1 etc. mu n, and if you count it with multiplicity, then you can say that let us say lambda 1 appears with multiplicity some L 1, and then lambda r say k appears with multiplicity L k. So, then it is clear that the characteristic polynomial of T is going to be the product x minus lambda I power L I range from 1 to k, and the minimal polynomial of x is going to be just product of x minus lambda I range from 1 to k with multiplicity 1, okay, because we can just permute the basis and then write this as the following blocks. Okay, let me just permute, then you will have lambda 1 etc. lambda 1, lambda 2 etc. lambda 2 and so on, then lambda k etc. lambda k. So, this will have size L 1 times L 1, this will have size L 2 times L 2, and this will have size L k times L k. So, now it is easy to see for each individual block you have only the minimal polynomial x minus lambda I, and the minimal polynomial of T will be the product of the minimal polynomial of each individual block. So, this is easy part. So, now we want to prove the other way. Suppose if you assume that the minimal polynomial has distinct roots, then we want to prove T is diagonalizable. Again it easily follows from the primary decomposition theorem. So, since MT of x can be written as product of distinct linear factors, so with multiplicity 1 assume all this lambda 1 etc. lambda k are distinct. Now, if you go back to the primary decomposition theorem, it says that if we set V I to be this generalized eigenspace which coincides with the eigenspace. So, this becomes eigenspace. So, in particularly V becomes the direct sum of V 1 etc. V k. So, now if you focus on T restricted on V I, then it is exactly lambda I times identity. So, that means if you take basis here B 1 etcetera B k and then put them together form a basis B, then with respect to that basis the matrix of T looks exactly what we expected, lambda 1 times identity on V 1 and so on, lambda k times identity on V k. So, this is going to be the blocks consisting of scalar matrices. So, in particularly this is diagonal. So, that means the T is diagnosable. So, this is indeed a very powerful characterization. For example, if we know you have an operator T inside endomorphism of V and assume that there exists some n such that T power n is identity on V. So, then from this you can immediately conclude that T is diagonalizable. Okay. So, that is because the T satisfies the equation x power n minus 1, and if you think about it, this polynomial x power n minus 1, the roots are nothing but nth roots of unity and they are all distinct. So, that immediately implies that all the minimal polynomial is going to divide this polynomial x power n minus 1. So, that means all the roots of the minimal polynomial, they must be distinct. So, that would imply immediately that T is diagnosable. And there is a very simple check one can do in order to verify a polynomial has repeated root or not using this derivative test. You can compute the derivative, and then if you are able to say that the GCD of the derivative and the original polynomial is 1, then that would imply f has no repeated root. So, this I will leave it as exercise. For example, here f dash of x is nothing but n times x power n minus 1. The only roots of the derivatives are the zeros. So, in particularly they do not have common roots. So, the GCD is 1. So, this theorem indeed gives very powerful way of checking something is diagnosable or not. So, but our ultimate goal is to actually find some simpler form that is similar to a given matrix A. So, how one can achieve that? So, that can be achieved, for example, using Jordan canonical form or National canonical form and so on. So, all we are doing is, so I already translated the problem in terms of the linear transformation. So, one can actually start with the linear transformation. So, this is the advantage of the abstract approach, and then what we are going to do. So, given this linear transformation, so we are interested in looking for a basis B of V such that the matrix of T with respect to the basis looks somewhat simpler. Okay. So, this is what we call, so whatever that simplest form, that is what we are going to call it the canonical form. Okay. So, we are looking for most simplest form from this set, all the matrices of T with respect to B. Note that if we change the basis, then these matrices are similar. If you go from B to B dash, then the matrix of T with respect to B and the matrix of T with respect to B dash, they are similar. So, indeed we do not lose too much information. And if we know how to track from going from one matrix to another matrix, So, which is coded in that change of basis. So, this is given by the relation is given by change of basis. If we record that, then we will be able to recover back the original matrix or the original linear transformation. So, in order to achieve this, okay, at least I am going to only discuss about Jordan canonical form. I will not be discussing about other things. Okay. So, we have this very powerful theorem called cyclic decomposition theorem. So, one can use cyclic decomposition theorem to achieve the Jordan canonical form. So, let me just recall or define the cyclic spaces and cyclic decomposition theorem. So, what is cyclic decomposition theorem is about? It is about writing given this vector space as direct sum of T invariant cyclic subspaces. Okay, so, we were actually looking for T invariant subspaces. So, I convince you that okay, to obtain T invariant subspaces, you have to actually look for operators which are commuting with the given operator T, and then you can take kernel of that or generalized kernel of that. So, they are going to give T invariant subspaces. So, that is one way to get T invariant subspaces. But if you think about it from abstract algebra, so one can actually get T invariant subspaces as follows. Okay. If we start with this operator T, what we can do? So, we can actually take some subset of V and then look for smallest T invariant subspace that contains S. Okay. From this, we can go for the T invariant space generated by that T invariant subspace generated by S. So, what is this? Theoretically speaking, we can simply take all possible T invariant subspaces containing S. That set is non-empty because V itself is one of them. So, you can take intersection of all of them. You take intersection of W, W is subspace of V, which is also T invariant, and S is contained in W. So, if we take this intersection, this is going to give you T invariant subspaces of T invariant subspace of V, which is generated by S. So, theoretically we can see that we can always get something using some subset of V. For example, one can start with just a vector and then take T invariant subspace generated by that vector. So, let us try to understand this. So, if this is actually generate T invariant subspace, then it is clear that. So, if we take T V, that is going to be supposed to be there in W, and then T applied twice on V should be there in V, and so on. So, if we take any power of V, that is supposed to be there, any power of T applied on V, that is supposed to be there in W for all k greater than or equal to 1. So, that means the span of all these vectors is going to be there inside this W. Okay. But it is easy to verify that this is indeed T invariant subspace. So, that immediately tells you that this is supposed to be the smallest T invariant subspace generated by V. So, that means this is exactly equal to the T invariant subspace generated by V, that is the intersection of all possible T invariant subspaces containing V. So, this motivates us to actually look for some spaces that looks like this, and we call them cyclic space. So, given V in V, you write the cyclic space as ZTV, which is the span of all possible T k v v k greater than or equal to 1 spanning over C. Okay, so this is what you call it as cyclic subspace. So now what is cyclic decomposition theorem says? So given T, so here is the theorem statement. So given T, which is acting on a finite dimensional vector space V, you can always find some vectors V1 etc. Vp from V, all of them are non-zero vectors, so they are not part of 0, such that you can always write V as direct sum of these cyclic subspaces. Okay. And this is called cyclic decomposition theorem, and moreover it satisfies the following property. If you call this Pi of x as the minimal polynomial of T restricted on this ith subspace, cyclic subspace. So then it satisfies the property that P1 of x divided by P2 divides P2 of x and so on, that divides P, okay, I will use k instead of Pk of x. P1 of x divides P2 of x etc. Pk of x. So these are called invariant factors, and they are uniquely determined by T. So these Vi's need not be unique. Okay, the cyclic, the choice of remark, the choice of Vi's, that is the cyclic vectors. So this need not be unique. But these invariant factors, they are supposed to be unique. And it is easy to prove that the minimal polynomial of T, that is going to be Pk of x, and the characteristic polynomial of T is going to be the product of these Pi's. And this also immediately tells that the minimal polynomial must divide the characteristic polynomial. So in particularly chi t of T must be 0. So now using this cyclic decomposition theorem, one can easily get Jordan canonical form. So first let me just tell you like what is Jordan block and how it is motivated from these cyclic spaces. So let us take as before, like so we already observed that one can write any linear transformation or linear operator as semi-simple plus nilpotent operator. So in particularly one can focus on only nilpotent operator in order to achieve the Jordan canonical form. So for that purpose, let us start with a nilpotent operator. Let us say acting on V. So let us assume that the nilpotency is R. So R is the nilpotency, which is the smallest power such that n power R is 0. So now if we just focus on one particular cyclic space, okay, so then what happens? So this is going to be the span of these vectors, okay, V, n V etc. n power R minus 1 V. So let us say the nilpotency achieved when you restrict to this subspace. Okay. So, then you can easily prove that this is indeed a basis. So, this is indeed a basis. So, in particularly what happens, so if you look at with respect to this basis, the transformation n with respect to this basis, the matrix of that is going to look like lower triangle 0 1 etcetera 0 0 0 1 etcetera 0 and so on. So, I am switching from upper triangular to lower triangular, but anyway it is a matter of writing, that is not a problem. And this is what you call a Jordan block, okay. So, which is denoted by let us say J R of 0. So, this is just follows from the fact that V is mapped to N V and then N V is mapped to N square V and so on. These are all the basis elements. I am looking at the image, and finally, N power R minus 1 V mapped to 0. So, that is why you are getting 0 here and then 0 1 0 0 etcetera here. Okay. So, this motivates us to define what is called the Jordan block. So, given lambda in C and R greater than or equal to 1, let us define the Jordan block to be the matrix which has lambda as diagonal entries and 1 just below the off diagonal and then 0 elsewhere. So, this is what we call a Jordan block corresponding to lambda of size R. So, now it is immediate that using the cyclic decomposition theorem and the primary decomposition theorem, we get Jordan canonical form of any given operator T. So, how do we achieve that? So, first to recall, we wrote the minimal polynomial of T, okay, which is acting on V as product of x minus lambda I power m I range from 1 to let us say k, where m i's are the multiplicity of lambda i's are all distinct. So, then we define this V I, which is the kernel of T minus lambda I power m I. So, then we realize that T minus lambda I restricted to this V I, this maps V I to V I, and this acts nilpotently on V I. So, now if we use cyclic decomposition theorem on this operator, so then you can write this V I as direct sum of cyclic spaces. So, let us not label them because it will get messy, but we have some decomposition of V I into direct sum of cyclic spaces. From each those cyclic subspace, we are going to get basis from those cyclic subspaces, and then putting them together we get basis of V I. So, let us call that is B I. So, B I is the basis, which is B 1 I disjoint union etcetera disjoint union B let us say D I, and this B S I comes from the cyclic subspace, the cyclic subspace. So, this is given by the cyclic vector let us say V S I. So, in particularly this is V S I T minus lambda I acting on V S I and so on. So, let us say the dimension of that space is K S I. So, then this is T minus lambda I power K S I V S I. So, note that computing these dimensions are not that easy. So, but we have an algorithm to do those computations. But we have this basis of cyclic subspace, and then if we put together these bases, we will get this basis of this particular ith generalized eigenspace. So, now what we can do, we can actually collect them together and then make a basis of V, which is the basis of V. And with respect to that basis, so we will be having the Jordan canonical form of this given operator T. So, to write down that, let us first actually focus on the blocks. So, the T with respect to B is going to look like blocks. So, this is going to be T with respect to B1 and so on, T B K. So, this is how the blocks looks like. So, now if you zoom in and then look at the individual block, the block of T with respect to B I, then this is going to be again looks like a blocks. So, with respect to B S I. Okay. So, the typical block here will look like T with respect to B S I. So, let us focus on this T B S I. So, this is actually coming from the cyclic space. So, this is going to be exactly the J lambda I of K S I. Okay, recall this is exactly equal to, in the matrix form, lambda i's on the diagonals and 1 on the off diagonal below this diagonal. Okay. So, this is actually coming from this following simple equation. If you take this T minus lambda I power some j applied on V S I and then apply T on it, then you get exactly T minus lambda I power j plus 1 applied on V S I plus lambda I T minus lambda I power j V S I. Okay. So, using this we get this, but anyway it is very simple thing to verify. I can actually leave it to you. So, from this you can see that if you actually start with general transformation T, then you can use cyclic decomposition primary decomposition to get first direct sum of eigenspaces, then you can use cyclic decomposition in order to get somewhat nicer basis, and with respect to that basis the matrix looks exactly like this. So, everywhere else is 0 here and only the blocks are focused, and if you see only the diagonal entry and then the one entry below that diagonal, that is going to have non-zero entries if at all. So, that means, so on the diagonal the number of entries could be n, and first off diagonal below that will have entries at most n minus 1. So, then the total number of entries, going to be at most 2n minus 1, which is indeed linear in n, okay, which is much more than what we started with. We started with matrix of size n by n. So, that will have entries n square, but we have actually conjugated it to some other matrix which has entries at most 2n minus 1. And if you ask me, like, this may have some benefits computationally, but going from this matrix that is A to this Jordan canonical form is not that easy, because there is this process that involves decomposing the minimal polynomial into product of linear factors, okay, maybe like one can try to locate the minimal polynomial using the characteristic polynomial. The roots of the minimal polynomial at least will be very clear, but decomposing the given polynomial is not that easy. Again, that is also a very hard problem computationally. Even if we do all those things, then we have to actually identify this matrix that is helping us to conjugate the given matrix into Jordan form, that P that plays a role. That is again very computationally hard thing to compute. But for all theoretical purposes, Jordan canonical form is very strong result, and we will use everywhere in mathematics in order to prove any theoretical results about matrices. Okay, I will stop here. So, this is somewhat most of the things that I wanted to tell about linear algebra. So, I want to tell you one more thing in linear algebra, that is a spectral theorem for self-adjoint operators. Maybe I will quickly recall that in the next class, then I can actually proceed to representation theory. I will stop here. Thanks.